right, I'm Robert, and this talk is about AUTOMAP. And if that means nothing to you, it's roughly how can you do NumPy-style broadcasting in a statically typed language. And it's in collaboration with all these people. Martin is here, if you want to also ask him questions that I can't answer. And everybody else, we're all from Denmark. So to start, you might have an operator plus to add two numbers together, and it just does this obvious thing on two scalars. But we might also want to add two vectors together with the same operator. And of course, it should just add them component-wise like you see here. Or we might want to add a scalar to a vector. And then we would broadcast the 4 into a vector itself, and then we would add the two vectors together to get this result. And of course, this isn't only just for binary operations, it should also work for unary operations. So here we have the square root thing, and we can apply the square root to a matrix, and we want the square root of every element in that matrix. And so the question is, how can we accomplish this in a static type system? And what this is sort of roughly called?
Closer to the microphone.
Sorry, okay. And what this is called rank-polymorphism, which is sort of the ability to apply functions to arguments that have different ranks than the function sort of naively expects. And this is mostly sort of a syntactic sugar type of thing. It just makes code nicer and easier to read. So for example, on the left here, we have what you would normally do in a language where you have to manually apply this map to addition across two vectors. And it's much nicer just to be like, hey, we have this vector, let's just add them together, and you can apply the operator infix, which is also much nicer. And in practice, pretty much every language that can do this happens to be dynamic. And so this talk is, how can we do it in a static system? And just to get started, let's first review how map works, which I think most people here know, but all map does is it takes a function f, and it takes some vector, and it applies f to every element of that vector. And our map is special, and then it can take multiple arguments. So you can take, for example, here we have plus, and we have two vectors, and it just does a component-wise addition between each component. We also have this thing called rep, which is like replicate, except you don't specify how big the thing is that you want to replicate, so it just makes some number. You can just think of it as increasing the dimension of the argument. So for now, we don't really care about how many elements are needed. In the actual implementation, we can figure it out in some ways, but this talk doesn't really talk about that. But it's a solved problem, so don't worry about the fact that we don't know how many elements we want for now. So an example of how this can work with map and rep is, for example, here we have a matrix, and we want to add a scalar to it. So what we first do in this elaboration is we rep the 1 twice to sort of boost its dimension twice and get a matrix of 1s. And then we map twice to lift addition up 2 dimensions to work on matrices. As another example, here we have 2 matrices, XSS and YSS. That's what each bracket there is a dimension, and then the underlying type is an int. So it's 2 matrices of integers. We have some function which takes a vector, a matrix, and it gives you back an int. And now we want f of xs, yss to work. And right now, of course, this is ill-typed. But what we can do is we can first map this f across both matrices. But now you've noticed that f, as its second argument, expects a matrix. But if we're mapping the f, and now it needs something that has rank 3, so we have to also rep the YSS matrix to make this thing work. And also in practice, these reps are free because you can actually push this thing down into a lambda, and then you don't actually have to actually implement the rep in practice. So our goal with this work is for any function application, the compiler should automatically insert these map and rep operations to make the application so-called rank correct. So what this looks like is we have some application here, f of x. We want to figure out how many maps and how many reps do we need to make this thing actually type correct, or at least rank correct, which is the first step to being type correct. And there are a number of challenges involved with this. So here is one example. So here we have a sum function, which expects a vector, and it tells you the sum of all its arguments. And we have this length function, which is polymorphic. So it says for any array, tell me how long it is. And we also have this matrix. And now we're saying, what is the sum of the length of this matrix? And there are many possible rank correct elaborations here. So for one, sort of the naive thing is, it's a little bit weird, but you can take the length of the matrix and you can replicate it to boost its dimension. One that you probably like more is this is first mapping the length across the matrix. So then we have a vector of length, and then we take the sum of that. But there are, of course, many more options. In fact, there are infinitely many more options. And a question that this work has to answer is, how do we choose which option? So Part of that strategy is that we have this rule, rule 1, which is that an application can be mapped or repped, or neither, but never both. So just to show what this means, this is of course okay, you have one map. This is also okay because you can have multiple reps, you just cannot have a map and a rep. And this is also okay, even though it looks like it might not be okay because it's actually two applications. We're first applying h to x, and then we're applying that whole thing to y. So it's actually two separate applications. So this is also legal under rule 1. But what isn't okay, for example, in this first example, we're applying map and rep to the same application, or again, the same thing in the bottom, just with multiple maps. And it turns out it's never necessary to map and rep in the same application to obtain a rank-correct program. So if you can get a rank-correct program, you don't ever have to do it both. So this is a fine rule to have, and it also reduces many of the possible options that an elaboration could be. As another way to reduce the number of options, we want to minimize the number of maps and reps that we insert to get a rank-correct program. So this has multiple benefits. First, it usually aligns with what programmers intend. We tend to write the absolute minimum number of maps and reps in practice when we write code. And it also makes for a simple mental model. So it's very easy to communicate to programmers how the elaboration will work. You just say, that's the minimum number, and it generally aligns with what they would do anyways. And importantly, though, that this minimization is over all the applications for top-level definition. So you can have, you define some definition on top level of your program, and there's a bunch of applications in it. And what we're doing is for every single application in the whole program, we're saying find the minimum across all those applications, not just individual ones. So it's actually a global minimization, at least at the definition of top-level functions. So if we go back to our sum length example, these are what we saw already, and we saw also these ones, and now we can eliminate those options. So now we've reduced the possible options to just these two. But another challenge here is that the elaboration is so-called global. And what I mean by this is, so in this first example, when we did the rep with the sum, we used sort of local reasoning, which is we applied length of xs, that works, that type, so we don't do anything. And then we tried to apply sum to this thing, and we go, oh, the dimension is too low. And so then we just insert a rep. So we're sort of considering each application one by one. But in the other example, when we use the map, this is sort of an instance of global reasoning in the sense that length xs is in itself rank correct. But if you also think about the outer sum, then you can sort of preemptively insert this map there because of the outer sum application. So what this really means is that we have to actually consider every single application all at once. And that is also another challenge. And yeah, another challenge, I forgot to mention this is about Futhark, but I'll get to that. This is the type system in question has parametric polymorphism, so we have type variables. And that makes things quite challenging because a type variable can have any rank. So we have no idea what the rank of this thing should be statically, and we have to sort of make a decision in that regard. And so we have this question of how can we statically insert maps and reps in the presence of type variables whose ranks are not known. And the way that we do this is with a constraint-based system. So suppose that we have this function. It takes some parameter type p, and it outputs some type b, and we have some argument of type a. So we're considering the application f of x. So in this application, we have this constraint, namely that the parameter type should equal the argument type. But in our circumstance, we only care about the rank. So we're going to relax this constraint to say the rank should be equal, where this double bar thing just means the rank of p. So for example, if we have this matrix type on the bottom there, the rank of this matrix is 2 because there's two brackets, and the rank of a scalar there, the int is 0. So in our context, we want to allow rank differences, right? That's what rank polymorphism is sort of all about. And the way that we can do this is, so there's two cases. The first case, so I'll remind you that p there is the type of the function argument, and the a is the type of the t there is the type of the function's parameter, and the a is the type of the argument. So you can imagine that the rank of the function, what the function expects, is less than what you've given it. And in this case, we can introduce this rank variable, m, which is suggestive because it's going to correspond to a map. And then we say that instead of having the equality before, where we want strict equality, we're going to relax the equality and allow difference via this rank variable m. So what this looks like in practice is we can have, for example, the square root function, which expects a scalar. We can apply it to this vector. And when we apply to the vector, and we look at the constraints, this says that because the argument there that expects is an integer, but we've applied it to this vector argument, we have this m plus 0 equals 1, so we find out that m equals 1, and of course, indeed, this would be rank correct, right? You can map the square root across the vector. And sort of dually to this, you can have the other case where the argument type is less than what the function might expect, and we do the exact analogous thing, except we have this rank variable r for replicate. And in this case, we're going to consider this example length. It's a little bit weird to do the length of 3, but it's just to illustrate how this works. And this would then yield this constraint. And interesting here, though, is that this b here right now actually is a type variable. And type variables can have any rank. So this actually has an infinite number of solutions. So one possible solution is we say there should be r should be 1, and then b can be equals 0. But of course, we can say r equals 2, b equals 1, and so on forever. So there are actually an infinite number of solutions here. All of these are sort of rank correct. And then sort of to summarize this constraint-based approach is, so for every function, every application of this function, so of a function of type from p to c to an argument x to a, we'll have this constraint, where now we've sort of have both m's and r's, because statically we don't know if the argument will be underdimensioned or overdimensioned or neither. So we have to account for all possibilities in that regard. Of course, we also had this rule, which we said that we can either map or rep, but not both. And so we also have this additional constraint that says either m equals 0 or r equals 0. And what we then do with these constraints is, so we collect exactly these constraints for every single function application and top-level definition. So let's, again, look back at sum and length. These are the constraints for length. And then these are the constraints for sum. And then, as you might imagine, we also had this rule too, which said that we wanted to minimize the number of maps and reps. And you might be able to see what's coming. That is exactly saying we're minimizing these rank variables that we've introduced. And this looks exactly like an ILP. The only thing that's not an ILP about it is the fact that the ORs are not linear, but you can linearize these constraints in practice using a little trick, but I won't get into that. So the way that the system works in summary is, so for every application in a program, we generate these rank equality in rule 1, which are the OR constraints. We transform these constraint sets into an ILP and solve the ILP with an off-the-shelf ILP solver. And then we use the solution to the ILP to actually elaborate this program. And when I say elaborate, so you can think of this application of X as having implicit maps, and now we're making those explicit. So here we found out that in this example, m was 3 and r is 0, so that means there's 3 maps. And then we have this program, which is completely elaborated. You can sort of think of it as it's not rank polymorphic anymore. And then you can just type check the elaborate program as usual and then continue with compilation. And the rest of the compiler can be totally ignorant of the fact that it supports rank polymorphism. So user experience-wise, map and rep are just normal source level functions. The programmer can just write them as much as they want, which means you can choose how implicit you want these things to be. You can insert them to any degree that you want, and you can choose to use the AUTOMAP system or not at will. There's also good ambiguity feedback. For example, there's no way to completely remove all ambiguity in all cases. So in this case, the compiler can't decide. So, but it's easy to show the user what the options are. You say, these are the options. You should choose one. And the way that they choose is to just insert either the rep or map themselves into the source level program. And of course, it's fully transparent. So you can have a program with implicit maps and reps, and you can be like, hey, tell me what it actually should be, and how it will actually elaborate. And the compiler can spit out the equivalent program with all maps and reps completely elaborated. So you can see exactly what's going on. So for the practical impact, so we've actually implemented the system in a language called Futhark, which we developed at the University of Copenhagen. It's a functional array language. It supports parametric polymorphism and top-level let polymorphism. Sort of difficult to quantify the usefulness of a feature which is just syntactic sugar. But what we did is we have a very large benchmark suite, and we took away maps whenever we thought it made it better. So as an example of this was a program in our benchmark suite, and it has a bunch of maps. It's kind of hard to see what's going on. It's kind of also hard to see the relation to the original math that this is actually implementing. Don't worry about the details. You can just see it's kind of a mess. And with AUTOMAP, it looks much closer to the actual sort of mathematics that we're trying to implement, and it's much cleaner and easier to understand. And average, so I'm running out of time here, so I'll just be fast, but this resulted in a compiler slowdown about 2.5 times, which isn't great. It's very unoptimized as is, but in practice, it's quite usable, even though we're solving many ILPs during type checking. And so in summary, AUTOMAP is a conservative extension of a Hinnerskov or style type system for array programming. Anything that can be inferred can also be inserted explicitly. So this is just like a classic type system, right? You can always insert a type annotation yourself, or you can have it be inferred. There's just sort of dual to that. We use some heavy machinery named ILP solvers, but the ILPs themselves are fairly simple, and in practice they're solved quite quickly. And while it is implemented in Futhark, it's not really production ready yet. So there's some existing work to be done, including speed, better ambiguity checking, and better feedback to the user. And that's it. Please check out Futhark at futharklang.org. There's a blog post that covers everything I talked about in much more detail. The paper is also there with a full formalization, and these slides and more about me can be found out on my website there.
Thanks for the great presentation. It was really interesting. So can you go back to the previous slide? Actually regarding the third bullet point. Did you look into features which are available in type systems of the languages like Scala, which is basically the implicit conversion and these kind of things? Perhaps actually you could kind of embed something similar in house languages like Scala with their type system. Have you looked into it?
I have not, but a reviewer also brought this up, but I didn't understand their question. So I don't quite understand yours either. Maybe we could talk about it after.
Yeah. I think that would be great. Thank you very much.
Yeah. So I'm not an expert in this stuff, but so I assume systems like NumPy do some kind of dynamic policy.
It's just all dynamic, right?
Yeah. So I'm just wondering,
the issue of really what makes this whole thing hard is the type variables.
That's okay. So I was just going to say, given the same program, you could do it in NumPy or do it using your thing. And I'm just wondering how these two policies, the dynamically determined one and the static one, would compare to each other.
So in NumPy, there's no, as far as I can tell, every implementation of an operator can do it differently. So there's no hard and fast rule. It's not that principled. This approach is, from what I understand, is much more principled than how NumPy might do it. You can also see what happens before you've run the program, right? Whereas in NumPy, it happens dynamically.
Thanks for the talk. I think it's super nice to see the verbosity kind of disappear. What I'm wondering is, from a usability perspective, when you are trying to debug your program, having so many things implicit and automatically inserted, how does this interact with that? Do you have any insights or experience?
Yeah. So there's always sort of this conflict, right, with implicit stuff. Is the more that you have implicit, the more that things can become ambiguous, right? So you've sort of changed the space of what this program can be. And it's just like in programming languages, very sophisticated type checking, in the sense that the way that you debug these things is sort of you insert manual type annotations until you sort of figure out where is this bug. And in AUTOMAP, the way that you debug it is you insert manual maps and reps until you sort of identified where the problem is. But in practice, we've actually found it quite usable and quite pleasant. And we've also found it that when we write something implicit, it almost always elaborates to what you would want to elaborate. So there was good alignment, and the quality of the programming experience is quite similar to what we already know with static type systems.
So can it handle something like adding 2 vectors of different lengths to infer, or?
That would no. In practice, that would result in a size error. I didn't talk about in this yet, but.
Thank you for the talk. So I'm curious how you guys decided to choose the term rank for this, because it means something else in the Haskell world, and I guess higher rank types and stuff like that.
You said length?
Rank.
Oh, rank. Yeah, rank just means the number of brackets in front of the type there, basically.
Right, but isn't that a clashing definition with how it's used in other?
Oh, I think you're thinking of higher ranked things, right? And
yes.
Yeah. I know there are many things called rank, but that's specifically higher rank polymorphism and not rank polymorphism. But I did not choose this terminology. This is existent terminology. It's old.
Oh, if it's an existing term, yeah, of course.
It's old stuff with APL. It goes way back.
Oh, okay, cool.
But I agree, it's confusing.
Thanks.
We do have time for one more question if we have one. We have one.
So you mentioned you had a benchmark. And you sort of took out some of the explicit maps, and then you went to see if it put them back in.
Yeah.
Did you actually do a systematic evaluation of erasing them and then having AUTOMAP, insert them and then comparing the programs, did you find that it would insert the original ones more often than not?
We were a little bit lazy with this, and we
Okay.
checked to make sure that the benchmarks because they all have outputs that you expect, right? And we checked that all the outputs are exactly the same.
Okay,
So we
that's
assume
good.
that with high probability,
Yeah.
it's very unlikely that you'd get two things that are not actually equivalent and had the same outputs.
Okay, yeah, that's pretty promising.
So
yeah.
we're quite, and we did it for the entire benchmark suite.
Great. Okay,
Yeah.
awesome. Thank you.